I'll let you know. It takes a few seconds.
Yep.
Now it should be recording.
Okay, I'll start this again. So I'd like to welcome everyone to the October Northwest C++ Users Group meeting. Again, we're all virtual, all hanging in there. Tonight's meeting is going to be a little bit different. We're going to try a panel discussion. So we've got three panelists here tonight. Myself, Andrew Sloss from ARM, and Brett Searles. And I don't remember your company, Brett.
Well, I have my own company called Atobotics, but I work for XKL, which works in high-speed communication, fiber optic laser communication.
Mm-hmm. And Brett, did you want to do any other announcements or anything before we dive in, or should we just dive in?
We do have CPPCon still going, Q&A sessions. We have one later this week. And also next week we have 2 or 3, and then the first week of November we'll have a couple more. So if you missed CPPCon, some of the presenters are willing to rebroadcast their presentations and then also ask questions. So I know like Chris Ryan has volunteered himself for one of them, so thank you. But if you're interested in either there is a registration link. I can put that in the email. And there also, if you would like to work on a Zoom call, so get more experience, we need some backup. So, but we do have all the main volunteers in place. So. Anything towards Northwest C++ Users Group? No, we don't have any sponsors or anything because we are always meeting online. So, no, I haven't heard anything from anybody. So.
Okay. Yeah, and on the note for meeting online, as far as I can tell, we are certainly going to do this through the end of the year, and it's looking like we'll probably do this. At least for the first part of next year until the Microsoft Reactor Room opens back up again.
Yes, but once we get that room back up, we will still have this online. So
that's right. Yeah, we're going to do this as a hybrid model going forward. That was actually the plan prior to COVID, and it just turned out COVID lined up with our plans. So. Okay, so I guess with that, our topic tonight, we're going to do a panel discussion. So what we'll do is, generally everybody, if you're not going to talk, go ahead and mute your mic. But if you want to say something, feel free to keep your mic open. It doesn't sound like anybody's actually generating, obnoxious noise at the moment. So we'll go with that.
Or you can raise your hand and rate.
Yeah, so if you want to jump into the conversation, I can actually see everybody on the list. So if you raise your hand, I'll be able to call on you, and it will kind of manage the traffic that way. So the topic's embedded systems. Take that where you will. That means, anything from what is an embedded system to how do you do it to what's the best processor to what are the challenges? We'll just kind of leave that as a open forum.
I think we're biased on that
one. So I think the next thing to do is let's just go around real quick. The three panelists tonight are myself, Brett, and Andrew. Let's just go around and introduce ourselves real quick, and then we'll just open it up. So Brett, do you want to kick it off?
Sure. My name is Brett Searles. I'm Vice President of the Northwest C++ Users Group, as well as the volunteer coordinator for CPPCon. And I've been working in embedded fields for over 20 years. I'm very interested in AR, VR, mostly holographics, actually. Working on a processor as well as the programming language with that. I'm also work for a company called XKL, which deals with 100, 200, up to 400, even 800G data. So people like in the movie industry want to be able to do on-site processing or immediate processing of film. So they want like 800 gigabytes of data to flow back and forth so they can actually process the same day. So that's some things that I'm working on right now.
Hey, thanks. Andrew, how about you?
Yeah, actually, you reminded me when you added a date. I have to go back and think, well, what is the date that I sort of started doing embedded? And I actually have the first board that technically I worked on, and this is the ARM1. This is one of the very rare ARM1 boards. And I was just calculating when you were saying a date. I was just calculating that
Pull that up again. I just put you in a spotlight so everybody can see.
Oh, right. Okay. Okay. You can see it there. Right. That was 33 years ago. Oh, I'm now feeling really quite in a different world. Now you've said that. So I've worked for, so I started my career working for an exciting company that developed the first ARM processors, not ARM itself, actually. It was another company. And in my early career, I built computers. That was the thing everyone did. Very few people worked on the processor side. And then about 24 years ago, I joined ARM, and then I've been with ARM ever since, and been following, the progression of the embedded system from a processor angle. So when I talk about embedded, I look at processors outwards. I mean, a lot of people look at peripherals and memory and look inwards, or I/O and look inwards. But my perspective is more on that outward from the compute side. And I've also been teaching embedded systems at the UW for now 15 years. I think this is my 15th year, which I'll do the winter quarter next year on embedded systems. And there's a lot changed. I mean, when I first started teaching embedded systems and what we teach now, just completely different. I mean, the hardware is just revolutionary different. I mean, you can't really, the new stuff doesn't, you can't teach what we used to teach 15 years ago. You've got to teach more modern techniques. So that's about me. I've been in the business a long time. I've been following things. I work in ARM research as my main role, looking at next generation technologies. So whatever we can do today, I'm not interested. I tend to look at all the things we can't do tomorrow, and so I'm employed to look at all the things, and that includes embedded and includes new types of memory. It includes all sorts of computation systems and all of that side of the world. So that's me.
Okay, and then I'll go ahead and finish it off. I'm Lloyd Moore. You guys all know me. I've been doing president of C++ users group for quite a while. My professional background is in biological-based artificial intelligence, but I've been working a lot in the embedded space for something on the order of 30 or 35 years, long enough I'm not remembering a whole lot of it. And I've also worked in many different fields, everything from industrial automation, video games, a little bit of entertainment stuff, and I'm currently working in aerospace. So pretty good breadth of different industries and so forth. In addition to doing the software, I also do digital design. And so I'll come at it from, depending on a project, I'll come at it from either a hardware or software perspective.
Right.
Which usually lands me right in the middle of the hardware and software development teams. So with that, let's go ahead and open up to the floor. If anybody just wants to jump in or raise your hand, and yeah, go for it, folks.
Or has a view. Sorry.
Chris
Hey,
Ryan
Chris.
here. I always have a challenge to people when they're going to talk about embedded and firmware. Define embedded, define firmware, and what's the difference?
Well, that's always a good question when I have a set of students in front of me, right? So I teach it every year. I go, so, okay, so why are you here, right? And what a great question, right? You know, and I've tried to work out the answer for a long time, to be honest. I come to my own, I guess everyone has their own realization, but I guess my realization is that really is his unique systems. You know, take out the word embedded. It's about building uniqueness for a unique problem. And, you know, we can argue about semantics, we can argue about all these other things, but in the end, you know, it's all the things that standard platforms aren't, right? It's everything. You're building uniqueness in some problem area, and that's what makes it exciting. Actually, that's what makes it a really super subject. It's not doing the standard, it's doing the non-standard. So as opposed to firmware, I guess I mean I think that's another one I would have said, which was really difficult to define, because it depends where you are in the chain. So some people view firmware as just the boot system, and that's it, right? And others view it as firmware being everything that is in the ROM, right? And you're either copying stuff from ROM into SRAM or DRAM and then executing out of that, or running from ROM, or all sorts of things. So that's a really good question, because I think, you know, there's sort of blurriness depending on where you are in the system, on both subjects, actually, both terms.
Well, I would consider firmware more to be like the HAL layer, sort of the interface between the hardware to the software that's going to be running on that, including the operating system. So you would basically write something that allows the software developer to easily utilize your system. Embedded, to me, yeah, I would say a standalone system that has a specific purpose. Specific purpose. However, embedded can have a specific purpose, but be put into a broad application. So it could be the peripheral to the processor. So I think it's basically the silicon to me, the silicon dioxide, or whatever you want to call it. I mean, in studying the, how to build a processor, you can build a capacitor, you can build a resistor, you can build inactive components as well as the transistors. So how do you want to create your system to meet the needs that you're trying to meet?
So from my side, I've always kind of looked at the intent. So for an embedded system, the definition that I've found useful is the intent is for it to be a closed single purpose system. And again, this is still somewhat fuzzy. Going back in time a bit, previous systems wouldn't have had an operating system on them for an embedded system, or at least the ones I didn't. Now that's completely untrue. Darn near everything runs Linux. I've got light switches here that run Linux. So that doesn't work anymore. But it's the intent of the system that it does one thing. The software that's loaded on it is a mostly dedicated load. And that's not even quite true either, because I worked on a gaming console at one point. So the software that was the gaming console, we considered an embedded system and treated it as such. However, the user could download additional games to it, which is just like you would do to a PC. So, in that particular case, we actually had a partition where, the games would load in one area, and there was a dedicated partition that was not open to that, and that's kind of what we called the firmware. So to the firmware comment, it's still kind of the same thing. Is the intent of that piece of software to remain a core piece of the quote-unquote appliance that it's been installed on, or is it intended to be modified or augmented by the user? And I've always kind of used that, and again, it's fuzzy. It depends on the system. It depends on where you're at. It depends on who you're marketing to. But that's kind of the guideline I've used.
Well, gee, they even say you can make embedded web apps, okay?
Oh, yeah. Matter of fact, and this thing did run some web stuff. Blurs the light.
Chris, I think it was Chris who asked the question. What,
Yeah.
you have a view?
Yeah, I also work in this area, and I have worked on game consoles also. It embedded requires it to be for a dedicated purpose, not a general purpose operating system. Typically, and like Lloyd pointed out, game consoles can load multiple different apps off of the web, and you can do a lot with them. They're basically a super high-powered computer. Some people try and limit embedded to mean something on a very small board or platform. However, on the game console I worked on, we had a multi-core ARM processor running a couple gigahertz with about 8 gigs of RAM. So that didn't necessarily apply. You got Raspberry Pis now that are basically a full desktop computer on a small board.
Yep.
So depending on how the Raspberry is used, if you plug it into a big monitor and a keyboard, it's no longer an embedded computer. If you have it running a kiosk, then it's an embedded computer. The difference between firmware is that firmware needs to have a non-volatile persistence, typically. And many times it is the lower level, near the metal type of stuff. However, that definition gets fuzzy when you go to download new firmware for your router. Your router is probably running something like a Linux. And the firmware is the entire OS image. And I used to kind of want to lean towards the direction of embedded being a very small computer with low resources. However, in a different life, dozens of years ago, I did a project for Philips ATL and did an ultrasound console system. It had 2 full PCs in it, running Windows. But they were in a dedicated purpose inside the box. The outside user never knew that what they were running, except for when it crashed, like the bank ATMs that you see all the time, rebooting into Windows. That was an embedded device because it had a dedicated purpose. However, it was a full general purpose computer. So that's why I try and pick this as a fight, because to throw it out, because some people try and say, oh no, it can only be an 8-bit computer with 4K of RAM. Anything more than that, and it's you're no longer embedded. So you and I are about the same age. When I went to school, we didn't have what we called embedded. We just called them microprocessors. Yeah. And we had big breadboards in front of us, and we wired them all up and hand coded them, the assembly, manually in hex in there. And to us, that was just yet another computer, whether it be a hard drive controller and a keyboard, whatnot. That's all it was, just a computer. But now kind of has to be a dedicated purpose.
I mean, one of the things, one of the interesting pieces is just cost has changed, right? You mentioned the Raspberry Pi. Here's a $35 device. It has capabilities of something that was sort of thousands of dollars. If you go back in time, in the embedded world, you never thought you would have that sort of power at that type of cost level. I mean, the reason you did a lot of things was because of cost, because you couldn't justify spending thousands and thousands of dollars. It's a very interesting field because economics absolutely affect it directly from that matter.
Well, you look at the space shuttle or even the Apollo, our microwaves have more computing power.
Yes. Yes.
Okay. So next one up, I see Robin has his hand up, so go for it, Robin.
Yeah, I have a question to Andrew, probably mostly. Recently, I heard about the plans by NVIDIA to purchase ARM holdings. Is there anything inside of ARM holdings that would be interesting for us to know? What do ARM employees think about it?
Well, you probably know exactly the same amount of information that I know. So one of the things, as an employee, you don't there isn't much difference. I don't think there's anything more you can add because this is the second time my company's been bought in the last sort of 8 years or actually probably 5 years. And I haven't seen much difference in any of the transitions, I mean, personally. And so I think, there may be differences in emphasis, but, the core systems all just go the same way. I mean, that's what I would say. I mean, I have no insight or no greater knowledge.
Will NVIDIA try to take over the IP of the graphics card and or the graphics processor and try to make their own image on that, or that's not in your?
Yeah. I mean, from my world's different. My world is looking at what happens next, right? So I'm looking at, my group looks at things like quantum and a whole load of other weird technologies that are coming along. And so that doesn't change where we are because those weird technologies are still coming towards us. Whether, at the end of Moore's law, I mean, one of the interesting things we've got is we've got the end of Moore's law, and we can debate that again. It's like embedded or firmware. We can say, well, what does that really mean? Well, it means the cost is getting greater to do geometry shrinkage. And so if that's the case, then embedded engineers are going to have to do a lot more work to keep the nice curves of improvement continuing in hardware, right? So that to me is probably a more interesting subject, actually. Because that affects our industry, that affects everyone in it. So.
All right.
I'm sorry, I don't. There's not much. It's a strange world, but that's not necessarily the world that I look at.
I'm curious. Are there any discussions about attempt to move people from UK to US or something like that?
No? I would be unaware of those types of things. Okay. We've got, I don't know what the breakdown in between the US and the UK is, but I mean, we've got places all around the world, actually. I mean, we've got a large group in France, for instance. It's all sort of, we're scattered all over the place, actually. Yeah. I mean, we've got people joining and moving all the time. We're a big, as a big company, you've got constant dynamic flow. I mean, when we were smaller, you could probably see it, but large companies, it's more difficult. Yeah.
Okay.
Okay. I don't see another hand. Does anybody else have something they'd like to bring up? Okay. I'm going to jump on. Oh, go ahead.
Yeah. Well, I mean, I got a set of questions. So there's Rust and Python and all these other languages coming up, and actually a re-emergence of Ada in the automotive industry. Ada's seeming, a language which I hadn't heard for a long time is sort of seeing some resurgence. And I'm an embedded guy rather than a pure C++ person. So the question really for everyone in the panel probably is do you see these languages and these changes having an effect on C++ in the embedded field?
I'll jump on that one actually real quick because prior to about 3 years ago, I was pretty dedicated, or pretty much full-time C++. C and C++ was pretty much everything I did. Going back maybe a decade before that, it was a mix of C, C++, and Visual Basic. Doing the Visual Basic would do the human-machine interface layer, and then C++ and everything would be below that. Just in the last couple of years, Python has come back into my realm fairly big, and Rust also, you mentioned Rust. Rust is also coming on fairly large. Specifically in the Rust area, it's around the various guarantees that it makes. So I'm currently, as I mentioned, I'm currently working in aerospace, and that's a mission critical, safety environment. And Rust is being looked at very heavily in those contexts for what it can provide. That said, a lot of the work that's been done in the recent C++ releases, C++ 17, C++ 20, I guess I should be saying upcoming C++ 20, is doing a lot of the same types of things. So the language aspect, and let me take one more dimension on that actually as I jump off. It used to be a project would be done in one language. That's something I'm also seeing now where, the current project I'm working on, while it's not necessarily the embedded part, the embedded part's all pretty much done in C. The support systems around it are involving everything under the sun. C, C++, Python, Rust, what else do we have in there? JavaScript at one layer. So as the compute power's gone up, the specialization of the language that you can use and the diversity of languages you can use is following right along with it. And it doesn't necessarily make for a simpler system.
I think that the real issue is memory. C++ still uses more memory than C, and C uses more than assembler. So it's depending on the performance and depending on the layer that you're really working at. C works with the bit layer much better than C++. However, C++ has its benefits in doing type checking and other techniques that other developers can easily incorporate into their applications. So memory is the key because Python's a JIT type compiler where it does a pre-build and then runs it on an interpreted compiler. C#, Java, same things. But there was one application that I worked on in Java, and then I did the JNI with C++, and I found that we were saving 10 megabytes of memory dealing with images, and it was a lot faster. So, and that was a smartphone, even though it had 8 gigabytes of memory, RAM, you still had to worry about power consumption. So, so it just depends on the environment that you're working with, really.
So, Chris, I see your hand up. Go for it.
Yeah, I was going to argue with Brett on the point that C++ uses more memory than C. It looks like it does, but when you get into larger applications, C++ is more efficient because of reused code. It can actually be a lot smaller than C, because in C, you have to repeat yourself over and over again, do a lot of stuff manually, a lot of cut and paste, a lot of introducing bugs. C++, you find a bug, you fix it in one place. All the side effects.
That is true, but it puts it in a data segment, which therefore you have to interpret the location of where the code actually is. So it costs you more in performance than with C, where C is all linear.
Well, except for the people that claim that vtables slow you down, there is a layer of indirection in vtables. However, they're still faster than doing pointer to function indirections in C. And because first of all, you have to set up all the pointer to functions, then you have to do the look it up and manually invoke it. In C++, it's all done in a couple assembly instructions, and you never had to get your hands dirty.
Yeah.
All done for you.
I mean, I think that's exactly true. And I think the more complex, I think C++ starts becoming, because it was designed for scale, right? And, you know, C really was never designed for scale. You know, it does that really good job of just doing that small bit of hardware, software interfacing. And it does it quite effectively, if not a bit dangerously. But the other thing I think I'm noticing is just trends in generations of people coming out of university, right? So you know, you need to be aware. You know, those are you know, the universities aren't really teaching very much C++ these days, or C. You know, the students I get who are electrical engineers are really good at Python. I mean, super good at Python. But you know, I have to reteach them C and low level coding in a course where I really want to teach them embedded. So you know, there's a trend here, and you know what I see with Rust and things like that is, you know, trends can get to escape velocity, right? And if they get to escape at velocity, then you know then they become the norm, right? And I don't think Rust has got there quite yet, but it's definitely got signs of it.
Well, I mean, there's more uses for web applications than embedded applications.
Oh yes, absolutely.
So that's why Python and Java are taught, because that's where the money is.
Yes.
But unfortunately, people do forget, oh, wait, I need the device to actually run it on in order to make the money. So, yeah.
You bring up an interesting point, Andrew, because I've noticed that with the younger developers I work with as well. You know, case in point, we were working on a project and we were essentially loading a log file. And I think, you know, based on our background and, you know, when we started programming, the way we would do this is, you know, we would load one line of the log file and process it, and load the next line of the log file and process it. And you know, iterate on this thing by line or by character or by record or whatever was appropriate for the data format. And these guys caught me off guard pretty well. They just loaded the entire 1 gigabyte file into a RAM buffer and dealt with it. You know, and I kind of looked at that and it's like, what? But it, you know, after thinking about it, it's like that is the mindset. They grew up and learned in a world where multi-gigabyte RAM is common, and you know, don't even think about the you know, the or the paradigms where that isn't common, and they just kind of go for it.
Well, that's the thing about C++ is the great thing is this STL and how they're really working with STL to make it more quicker in performance, and so there are advantages to C++. And as one of my esteemed colleagues said, he says you can't do everything in one language. So just try to get the best out of each one of them. And so to answer your question, Chris, yes, C++ does do its great work with lists and structures and things like that, and type checking and you know, templates and things. But there's advantages to it where Java is more advantage to web, and C# is more advantage to web development.
And I will give you that everything being a template these days and it's reinstantiated, becoming very flat, does cause a lot of memory bloat.
Yeah.
So that is one spot where it comes back. We're good at using old polymorphic mechanisms, which everybody thinks are nasty and awful now, which I still love.
Yes.
Those will reduce memory. And all these people that are absolutely against any object-oriented say, no, we have to do it in C. A lot of operating systems are written in C. A lot of device driver models are in C. Device drivers are very, very object-oriented. They have a handful of methods. You pass it a handle to that and a couple parameters. That is an object you're treating via handle in C, if not assembly. Yeah.
Right.
Yeah.
Well, we also have to worry about serialization of memory, because Unfortunately, I'm working with COM. I remember my days working in COM. You couldn't write a function twice to save, or it'll say I can't compile. So yeah, so so it's what language depends on what
Yeah, and the different levels.
Working.
And the different levels of embedded. I mean, some embedded, you cannot use malloc, you cannot use dynamic memory. You don't have, and that immediately shuts off a large bit of different programming languages, right? I mean,
Right.
you are limited to a very, very strict way of programming, and everything's static, right? You can use malloc before you finish initialization, but once initialization is complete, that's it. That's the end of your use of that dynamic memory. And so, different.
That's the critical systems like space industry.
Right.
You can't use dynamic memory.
Right.
Yeah.
Yeah.
Okay. So I've got a question in the chat window here from Skeets. So I'm just going to quote him. Or her. I'm not sure who I'm quoting here. But anyway, my background has been in the services application SDK level, but I'm looking into changing teams at my company. That would put me closer to the hardware. What would you recommend for someone new to embedded development, and what would be the first things to learn?
That's like what is embedded and what is firmware.
Well, a little bit, but
Yeah.
I think this one's targeted to you, Andrew, because you're the education.
Yeah, I mean, if I was starting today, right? I have very little experience and I want to learn. I think I would look at Arduino actually. I think that's a C++ environment, and they simplify it. They simplify the problem space, but it gives you a relatively nice platform. The hardware's relatively cheap just to get that experience. A lot of embedded, the excitement is just getting a little LED flashing on and off. I mean, a lot of the higher level software is all wonderful and AI, machine learning and all the rest. But a lot of embedded people get super excited flashing an LED on and off, because that shows that we've got the hardware up and running to a level that we can start operating on it. And so, Arduino is a good thing. It depends what level your company is at, because, some, as already described, some embedded devices are pretty capable. They're much more advanced than just simple microcontrollers. So you'd need something, a bit different. I don't know what's offered on Intel side, but, in the ARM space, there's things like the Raspberry Pi and things like that, which you can look at from that angle. But, these are pretty powerful devices. So it depends what your company is working on. But Arduino is a nice, I think. To get going, at least.
I think another piece I would tag onto that is, at least when I'm looking at, working with embedded engineers, one of the things that sets them apart from your typical software engineer is the ability to do two fundamental things. One, deploy to a remote system. So the system that you're developing on and the system that you're targeting are two separate systems. So look at that aspect. But the other one is the ability to interface with hardware, understand hardware, and essentially even just something simple like look at an oscilloscope and understand how that's relating to your code. I think what you said with Arduino and Raspberry Pi are dead on. They're great spots. I would also add, though, if the group that you're looking and moving into is more hardware focused, you can pick up little USB oscilloscopes for under $100 now, and they're simple and they're straightforward. But as a learning tool, if it's relevant to where you're going, in some places it is, in some places it isn't. But in the embedded space, I find that capability very valuable.
I think it also depends on the compiler you want to work with. There are some, like Keel has a compiler that will let you see into the registers and how they're working with the code. It shows you the disassembled assembly, things like that. So when you're looking at a sheet like an I2C bus or looking at something else, you can actually see the bits moving as you're going through each line of code. So if that's what you're wanting to figure out is some kind of like communication protocol, get the design specs for that, and actually get a good play compiler like a Kyle compiler. Get an Arduino. There's a TI. It has an ARM M4 chip. It's only like $12. You can just start typing code. It will show you the disassembly. It will show you the registers. And the call stacks, things like that. So you get a good understanding of what you're reading from the spec sheets, design sheets, to what the hardware is actually doing.
Yeah, I mean, the other one which is really fascinating is how hardware switches on, right? You know, the actual process of the first line of code that gets executed to actually having a running system, right? And, I remember teaching that side in a course, and we had people who had gone through 4 years of a degree, but they'd never dealt with that. They'd never dealt with that first code segment of initializing a piece of hardware. You know, that was missing in there. And this is where embedded people, you know, that's one of the most interesting things is how hardware switches on, you know, how the memory is laid out, how you set the pins so they're stable. And you're absolutely right, Lloyd, about the tools, right? That separates a normal software engineer with an embedded engineer is all the use of the tools and JTAG, which Alexa, the brand, you mentioned JTAG, looking at all the registers and all of that. That really is the difference. You know, it's the use of these other tools to help you bring up a piece of hardware. I think these are both great points, right? And be comfortable with them, right? These tools.
Actually, look at a company called Diligent. You find them on the web. They sell a plethora of little single board computers, FPGAs, tools, JTAGs, and they're all targeted at the education environment, so they're not expensive. Yeah,
it's super fun. You know, this bit of embedded. You know, it seems odd, but and confusing. But once you get over a little bit of the confusion, it's one of the most really interesting areas because you're actually understanding how hardware switches on, how hardware works. You know, it's a super exciting area in the embedded field.
Yeah, I mean, I was like showing my son how to do this, and I was salivating. I was like, "Wow, look at that! Oh, look at how the interrupts and the interrupt vectors loaded from the ROM to the to the RAM."
Yeah. Okay, I've got a hand raised by Bob. Go for it.
Okay, I just wanted to bring in another sort of point of view that dates me and differentiates my kind of embedded, or the kind of embedded that I've had contact with, which started with a data acquisition system in a physics laboratory. That was based on what was then a mini computer. It was the size of a refrigerator. This is the 70s, and with all of its peripherals, it was an office-sized room with 32K of 24-bit memory, so it was very small by today's standards, and with at a clock rate of 1 megahertz. And
slow down.
But it was state of the art in the early 70s, and but there was a lot of hardware associated with it, custom built interface boards and wire wrapped panels and all these. good things. That is just a little, that's just there for a little history. But and all of the embedded systems I've had a contact with, although I haven't been doing very much with them myself, but I have a contact with them since then, are data acquisition systems of various types, and they're not necessarily small in the sense that we're mostly talking about here. That a dedicated data acquisition system for a Navy sonar system with 1,000 channels of sound is a rack.
Yeah.
And with a whole lot of dedicated hardware, and running some version of Linux usually. But the sort of general idea that an embedded system is a small system, I'm just mentioning these things to challenge the idea that embedded systems are small systems.
Yep.
I don't have a whole lot that I can say about.
I mean, I think you're right. I mean, I think the scale. I mean, what from a teaching angle, we've spent a lot of time teaching the low-level core, interrupts and exception handlers and memory and all of this stuff because that's a missing piece. So we're forced to use lower cost hardware just because that's a missing piece of teaching, right? But you're right. I mean, it goes right up to these really big systems, and actually, I've been teaching for the last 5 years on this other world of this much richer embedded environment, because I used to teach all the low level stuff, and I did that until I go, well, this hardware is getting so powerful, you can do some serious pieces of engineering with it, and hardware's come up, and you're right. There's these absolutely larger systems. And there's no doubt about that. But I would also question, though, the one thing I would say is not just data acquisition. A lot of embedded systems actually control actuators. They actually do the opposite. They're actually affecting the physical world. They're not just recording it. They're doing things. I mean, that's what makes them dangerous. Actually, is when they're doing things, right? So there's that element. But you're right. It's such a big field. Absolutely these dedicated larger systems, right?
And many of those are closed loop. They're doing things.
Right.
Take the data from the sonar systems and doing things with. I mean, there's torpedoes, for example, that that's all I'm going to say about torpedoes. Yes. Those are data acquisition systems that do things.
Yes, let's not tell anybody anything where we have to kill them afterwards.
Right. No, there's no secret about that.
I had a really good lecturer who I brought in on my course and to teach one particular thing. And what they did was they built this sensor to work out the erosion of beaches. The sand erosion of beaches. So they built this sensor. What I loved about him was, he came into this idea and he goes, well, I'm just going to have a very powerful processor and it's going to take all the sensor data and, and then analyze it. And he built this thing, and it was something the UW sold. It was actually erosion. It was one of a unique product that the UW had as a prototype you could buy. And then he realized what a mistake that was, and how distributing the logic was actually the most important thing. So each sensor had its own CPU and actually filtered the data that went to the data capturer. So it'd gone through this process, and I brought him in just to explain, just having a huge, great big processor doesn't necessarily make this a helpful design. You have to distribute the way you're collecting the data and how that data is coming in through these systems. And quite a unique thing. But going to your point, you've got these big things to collect the data, but you've also got the little things to sort of help collect, monitor and collect the data in the way that it needs to be collected.
Right. And in between are these autonomous vehicles which is another type of embedded system.
Right.
My contact is with those that run under the water, data acquisition systems, not non-military, mostly, and they tend to be single board Linux computer driven.
Right.
That have closed loop processing. They sense their surroundings and do things to modify their behavior.
And you guys are both getting into an area that I've seen as well, where we're talking about we call it embedded systems.
Yeah.
And to a degree we make an assumption that it's one computer, and historically it tends to have been one computer. What I'm seeing now, however, is if you want to put the emphasis on the system word.
Yeah. System.
Many of these systems, and I'm speaking autonomous vehicles in particular, and some spacecraft, have multiple embedded computers on board with an embedded network, all working as one system. And that of course brings in a whole nother level of engineering to it, because you're not just dealing with one thing, you're dealing with multiple platforms, possibly multiple different processor types, possibly multiple different operating system types, all interacting as one large system.
So I guess embedded, has gone from just the single processor to embedded systems. So to answer Chris's original question.
Well, and to date myself further here, was just today I actually digging out stuff over the weekend, and I found a tube of 8032 processors.
Mm-hmm.
It was for a keyboard project I did well over 15 years ago. Like, they went to the recycle bin, but it's like that used to be an embedded system.
Right.
Right. One chip, everything on one chip. That used to be a big deal. And now we're back to, talking about systems that, have, multiple whole computer systems tied together with a network as an embedded.
Yeah, I mean, Boston Dynamics is a beautiful example, right?
Yeah.
I mean, they have loads of MCUs controlling all the different parts. I mean, and then they have the bigger computer is actually used to make the planning side of it. It's not to actually control the device. And that's there's a whole load of those distributed sort of embedded worlds. But I like bringing him in just to show that point of him going through the process. Let's put a big processor in there. Oh, that's not particularly useful, and he ended up having all these bottlenecks, and then he had to redesign with smaller systems.
That's an excellent learning environment, or an excellent learning point.
Yes.
Okay, somebody else. I don't see any hands. Let's see. I had one I was going to bring up a few minutes ago. I'm trying to remember what it was. So let's talk about scalability and power consumption for a little bit, because that's one thing it's actually one of my interview questions, is power consumption and code efficiency as with respect to power, because a lot of embedded systems are not plugged into the wall.
Right.
So you're looking at a different level of resource constraint than you would typically get with a desktop application, although server applications also have power considerations. Anybody want to jump on that topic?
And it's particularly hard in software, right? I mean, the tools for probing how much energy you've used between 2 points isn't like counting the time, right? The probe devices are, you've got them, but they're not exactly in a way that is nice for programming. I think it's interesting. I think power management and power control is still an art form, hasn't gone to a science. You can't go and buy a book on power control in C++ or something like that. I mean, there's no, the theories, are still, I think, relatively primitive because, the tools are primitive and it's not like performance.
Well, I remember when Walter was saying, we've been doing this for 20 years. How come we can't figure it out? Well, it's chaos, It's how, I mean, like the gates are getting shorter and shorter to 3 millimeter, but then you got to consider, now you've got leakage from one to the other,
Exactly.
things like that. So yeah, you can make the transistor as small as you can, but then you got other things to consider. So you got to deal with chaos, and you can't. Power cannot handle that all the time. So
yeah.
And again, it's another one of these non-intuitive things. In the simpler days, it was, turn the thing on, get your stuff done, and get it turned off as fast as possible.
That's right. Yes.
And now you must consider if you've got any type of dynamic voltage and frequency scaling, that rule really doesn't necessarily apply anymore. Sometimes you're better turning yourself on really slow and get it done because your voltage could be lower and your leakage is lower as a result. And sometimes that's not the right strategy, so you kind of have to go measure it.
Yeah. I mean, there's a nice way to think about the equation, the dynamic power equation, right? If you take a look at it, because of the closeness between frequency and voltage, you can sort of say that power is proportional to frequency cubed. I mean, you can take this blinding step, right? And then you realize how important it is to bring down the frequency, because that's the killer in most systems, is actually the frequency. And that's why you saw companies going to multiprocessor and SMP and all this other stuff rather than raising the frequency higher, because with an SMP system you can shut them down as complete units of drawing power, right? And to me, as I said, I always look from the processor perspective rather than anything else. And the processor perspective is, try and bring down that frequency as much as you can, because it has such a controlling point on the power consumption.
Yeah, and I've run into that where that generally works, but you need to look at basically your startup and initialization time as well. If you've got a system that takes a significant amount of time to come out of a sleep state, then so it's this multi-dimensional problem that you really have to look at all the aspects in that particular system. And I think, to your point, Andrew, build a model.
Yeah.
Get the formulas, build a little model, and then either a prototype actual model or a mathematical model, and work through it.
You got to be careful of the watchdogs.
Yeah.
Yeah. The other thing, looking at power, is always lots of little things. There's a set of big hammers that you can control, but there's all these little hammers that make, as you collect them all together, make a difference. And so it's a hard thing. I remember one company, which will remain nameless, had a major problem with very bad performance on batteries, and it turned out to be the battery monitor itself.
Oh, jeez.
Because it kept waking up the system to find out what the state of the battery was. And it was the thing drawing all the power, and it wasn't actually any of the clever technology that they had added in the rest of the system. It was a lesson learned.
Yeah, I've run into several like that where, so I used to work in a cell phone group.
Yeah.
And I was in charge of battery power consumption for the team for a while. And the really counterintuitive piece was when you look at a system level, the biggest power consumption was not the radio. The radio was the biggest instantaneous power consumer by far. That thing would turn on and suck amps. It was not the processor, because it would pop up and go to sleep and do its thing. It was the backlight. because it was on at a moderate level all the time. So the biggest single power consumer was the backlight.
Yeah.
And that was it was a non-intuitive thing until you kind of realize
exactly.
You're looking at the integration of that power over time, and it's not
Power is a fascinating thing in embedded. I think it truly is. It's one of the hard ones. And as I said, it sort of is in some ways an art form, and it can be really, really difficult set of problems. And your software, as you design your software, if you're designing your software with a fixed frequency and you're designing it for a variable frequency, that's a very different. You take any of the protocols for communication, you take anything like that, and you're varying the frequency, the underlying frequency of the device. You need to be able to adjust to that frequency changes, and that's non-trivial. That's a non-trivial piece of engineering.
Well, that goes back to your whole system and how you have like the one guy with the one processor probably had a huge power drop because it was doing everything at one spot. But when he separated it, I'm sure it decreased the load. So
right.
If one sensor wasn't taking any data, it was down, and the other ones were doing it. So yeah. So you have to look at the whole system, not just one piece at a time.
Yeah, and there's regulations in the power world too. I mean, in Europe, standby means standby, and it doesn't just mean a light that just stays on saying it's on standby. There's a whole load of deep regulations, even for the tethered systems in power, right? It's not just, in battery, I think you've got you're trying to get the most out of very little energy coming through the system, but in the tethered world, you've got equal problems on regulations and things like that.
So here's an educational question for you, Andrew. How much are students getting for looking at a whole integrated system these days in the education side? That's one thing I noticed, that students tend to be fairly focused on the individual pieces. And well, I shouldn't say students, I should say young engineers tend to be focused on the individual pieces and not necessarily a holistic systems perspective.
Try to think about that. I think I tell you the bit that I think is difficult in education is actually some of the real details which aren't being taught, right? So and I'm not going to blame education. Education's got its different problems of different eras of professors and different whole load of different places, but one of the difficulties, as I said, that initial code to switch on a piece of hardware, very few people have actually been ever trained in that. Yeah. But it's like an important thing for people to have an experience to understand how, if you want to do embedded, that's one of the most interesting pieces to look at. Or, how does a processor actually work? How does it fetch, an instruction? I think it was Chris who mentioned building, systems, that actually did that primitive, processor fetching and things like that. If you don't get that experience of how hardware grabs an instruction or how it grabs memory, you're missing a very important piece, and it makes embedded very confusing because you're not sure how these bits work. And so then you bring it up to the system level where they may know a huge amount on TensorFlow Lite or one of these new ML libraries, but they don't know how things are fetched and how to make that efficient and how to align the fetches all together. And there's all the caches. If you got caches, it becomes even more complicated. So It's difficult because, so few people were ever trained in this area and so little is actually written about it. These core pieces.
When I first started learning, I was fairly young, junior high type level. And my dad was going through a computer programming course at Boeing in Fortran.
Mm-hmm.
And one of the things I got interested in at that time, he brought home a cardboard computer. Have you ever heard of a computer called?
Yes, I've seen one. Yes.
It blows my mind. Nobody has brought that back into the teaching world. Yeah. It was absolute. Anybody on the web, just look up Cardiac, C-A-R-D-I-A-C,
yes.
Cardboard computer. You can get an image of this thing. You might even be able to get something you could print out and use. It was an amazing tool for showing you how assembly instructions got processed, including the fetch, the process of the cycle through the ALU and back to memory. And for everybody else, essentially what you did is you wrote your instructions down on little erasable, with pencil, like pencil and eraser type, not erasable memory, but and then you would slide, your instruction would fall into a sliding window, and you would decode that instruction. That would tell you how to move the next sliders, and that would route the registers through. And you would carry this out with pencil, essentially pencil and paper, with this cardboard tool. And it was fascinating how all that worked. And I have not seen anything like that in decades in any engineering program I've ever seen.
And I've seen that once.
It just kind of fell off the surface of the earth, and it was a wonderful teaching tool.
Yeah,
I had one of those too. It was cool, definitely.
Yeah. And now we've dated ourselves, all of us.
Actually, I saw someone who'd built a recent version of that. I didn't see the original, but I was at a strange event of investors, and he had actually built this for himself because he thought it was so important that someone should keep this thing alive. And
it's floating out there somewhere.
Right. Yeah. That's a very interesting. But but it's difficult. And also the hardware's got so complicated that if you had to explain a modern piece of hardware, it would take a lifetime to understand how it's all put together. But the simple stuff is sort of that's
those fundamental principles still hold. They're all dressed up, but the fundamental principle's still there.
Yeah.
Okay. Well, folks, we're at 8:15. People, I'm not seeing any more questions. Do you guys want to call it a wrap, or do you want to keep going? I'm not hearing anything, so I guess we will call it a wrap. Thanks, everyone, for showing up, and I hope this was entertaining. Feel free to drop me a note. I think, at least from my side, this seemed to go pretty well, so I think, if we do some panels in the future, this would work. This was kind of an experiment. We had originally planned this to be in person. Clearly not happening, so we decided to try it online, and I hope everybody enjoyed it. Thanks. Thanks to Andrew and Brett as well as panelists.
All right. Thank you.
Thank you.
Talk to you soon.
See you, folks.
Thank you.